So, in the last class we saw commuting family of self adjoint operators finitely many, and we proved a spectral version of spectral theorem for that by realizing the jth operator A j as multiplication by xj, the coordinate function xj, on some subset of Rn, right. We will continue with this theme. We'll prove the same result meaning spectral theorem for finitely many commuting normal operators, bounded normal operators, exactly the way we will use whatever is already done, that means the result for the self adjoint operators we will use that, and we will get a more or less the analog statement that instead of multiplication by xj we can allow multiplication by zj's, where zj would be the jth coordinate of let us say z1 z2 zn, but now the domain is going to be something sitting inside Cn, right. This is the difference which you have already seen in the case of the single operator. If the operator is self adjoint, then its spectrum is contained in the real line, right. Otherwise, it is a subset, compact subset of the complex plane. So, if I have n operators, I am going to get a compact subset of the n dimensional complex space Cn, right. In the case of self adjoint operators, I got a subset of Rn, right. So, that is the difference, but one can use the result for self adjoint operators to prove result for normal operators. So, before we get into the general case of commuting family of normal operators, let us revisit the case of the single operator case and try to prove it using whatever we know about self adjoint operators. Okay. So, let us quickly do that and then we will go to commuting family. Okay. So, let us start. Let A be a bounded normal operator, So, bounded normal operator. So, A star A equal to A star, right. So, that is my operator. Let us do the cyclic case. So, let V in H be a cyclic vector for A. Okay. What does that mean? That is you look at polynomials in A and A star. So, you look at polynomials in A and A star, they commute. So, there is no problem in writing down any polynomial in A star. You look at its action on V and you look at the span closure, that should be your Hilbert space H, right. This is what you mean by a cyclic vector. So, essentially it is A to the some power A star to the some power acting on V and take the span and take the closure, right. These are same. So, maybe you can write it like that as well, A to the j, A star to the L acting on V, you take the span closure, right. J and L go from 0, 1, 2 etc., right, and you take the span closure. These are same, right, because when you take the span of those monomials you get all polynomials. So, in the cyclic case you can well we want to say, so claim is that there exists a unique measure, because the cyclic case, right. So, the measure you can say is unique, let us say mu sub V, okay, on the way we are going to write down is, so you look at all those z in the complex plane. So, now because it is actually the spectrum of the normal operator A, but we will write it down as modulus of the real part of z less than or equal to norm A, comma modulus of imaginary part of z less than or equal to norm A, less than or equal to norm A. So, as a set, what is this? This is the set minus norm A to norm A cross minus norm A to norm A, right. So, in R2, right, which is complex plane. So, this is minus norm A to norm A and you take the product with itself, right, minus norm A to norm A. This is how the domain looks like, and so you have a measure supported there. If it will be actually supported in what is known as the spectrum of A, that you already know, but in the formulation we may not bother about that. Okay. On this space such that, well, what is the importance of the space? The operator A can be realized as multiplication by Z, right. So, in the self adjoint case it was multiplication by X, right. So, A, so there exists such that, well, maybe I should say and a unitary U from H to L2 of this space, right. So, this is minus norm A to norm A times minus norm A to norm A with respect to the measure mu, such that the operator A becomes multiplication by Z, right. So, U inverse, so U inverse will take L2 to the Hilbert space H, apply the operator A, that you are still in the Hilbert space H, apply U again, you go back to L2, right. So, this should be acting on some function in L2, and I should tell you what it is at some point Z, right. This is Z times F Z. Okay. So, it is multiplication by Z on L2 of mu, right, because of the cyclic, otherwise you take a direct sum and then do the same thing again, right. So, A is unitarily equivalent to multiplication by Z, right. So, M by mz I mean multiplication by Z, and so A star will be unitarily equivalent to multiplication by Z bar, right. If I look at the adjoint of this operator on L2, it is simply multiplication by Z bar, right, and then you have the continuous functional calculus and things like that. Well, so let us prove this quickly and then we will go to the commuting family. So, proof, well, we will deduce it from whatever we did for self adjoint operators, that to the commuting family of self adjoint operators. So, where are the self adjoint operators? A is normal. So, you look at its real and imaginary part. Okay. So, write A equal to B plus IC. Okay. What is B? So, B is going to be A plus A star divided by 2, right. We did this for compact operators, right, it is essentially the same argument, C equal to A minus A star divided by 2I. Okay. Then C and B and C are self adjoint, C star equal to C. They are self adjoint and they commute, right. So, B C equal to C times B. Well, why is that? Because A is normal. So, A and A star will commute. So, here it is A plus A star and there it is A minus A star. So, you know that they will commute. Moreover, they are self adjoint and norm of B, well, norm of B is less than or equal to norm of A plus norm of A star by 2, but norm of A star is norm of A, right. So, it is 2 times norm of A by 2. So, I will have a norm of A here, and similarly norm C is less than or equal to norm A. Okay. So, if you remember the domain for commuting family of self adjoint operators, it was minus norm Aj to norm Aj, the product, right. So, here I have both bounded by norm A. So, that is why I have the product of the intervals minus norm A to norm A. Okay. So, by the previous result, well, what is the previous result? Previous result is for a family of self adjoint operators commuting, right. So, I have the commuting self adjoint operators here B and C. So, B and C can be identified as multiplication by x1 and multiplication by x2 on L2 of minus norm A to norm A times minus norm A to norm A with respect to some measure, right, in the cyclic case, right. So, by the previous result there exists a measure mu, right, because I have a cyclic. So, there is only one measure, otherwise you take the direct sum. Okay. So, I will leave out that part, we will do that in the general case. by the previous result there exists a measure mu on minus norm A in fact minus norm B cross minus norm C right, but both are less than or equal to norm A. So, cross minus norm A right, this is sitting inside R 2 right in the complex plane. Okay. So, there exists a measure mu such that the operator B is identified with, that means there is single unitary right. So, maybe I think it is better to write it in full detail. By the previous result there exists a measure and a unitary from H to L2 of this space right. So, minus norm A cross minus norm A with respect to the measure mu right, mu VV such that B becomes multiplication by x 1, C becomes multiplication by x 2 right. So, U inverse U inverse B U acting on F at the point. So, there are two coordinates right. So, x 1 comma x 2 right equal to. So, first operator is multiplication by x 1 right, f of x 1 x 2 and U C U inverse f at x 1 x 2 is x 2 times f of x 1 x 2 right. So, I want to know what happens to the operator A right, but what is A? A is B plus I C right. So, A equal to B plus I C right, and so if I look at U A U inverse right. So, acting on F at the point x 1 x 2 would be well I have B and C. So, that is x 1 plus I x 2 right. So, it is x 1 I x 2 times f of x 1 x 2 right. So, this is what we write in the complex notation to be x 1 plus I x 2 will be your z right. So, it is z f z right. So, that is why the operator A is identified as multiplication by z on your L 2 space right after identifying R 2 with C. Now, we can prove. So, next we will prove the commuting family case. Okay. So, next we prove the spectral theorem for commuting family of commuting normal operators. Okay. So, commuting family of normal finitely many. Many of the statements are true for infinite families as well, but we will not be getting into that. So, before we go to commuting family of normal operators, let us go back to the self adjoint case. There was a crucial fact there we used right. We formed the Riemann sums and then the limit of the Riemann sum existed because of several reasons. One is these projections of different operators, the product of the projections of different operators commuted right. They were commuting because the intervals were disjoint. Okay. And well the projections associated with A. So, let us take two operators so that it is easy to explain. If I take A1 and A2 self adjoint, the projections associated to A1 will commute with projections associated with A2 because A1 and A2 commute, but there they were self adjoint operators. So, the star did not matter, the taking the adjoint did not matter. So, the commuting came easily, but here we have normal operators. So, to show that the projection, so when you say projections you are already going to L infinity functional calculus for each operator right. So, let us take two normal operators A1 and A2. I want to say if A1 and A2 commute, the projections associated to A1 and A2 will also commute right. So, that requires so if you recall some of the results we did in the beginning, an operator commutes with the projections if and only if it commutes with everything coming from the L infinity, if and only if it commutes with everything from the continuous functional calculus, right, the star algebra. But in the continuous functional calculus you have both A and A star. So, you need to show that if something commutes with a normal operator A, it will also commute with A star. Then it will commute with the algebra generated by A and A star, which will give me continuous functional calculus. So, the operator commutes with continuous functional calculus, and then you can go to L infinity functional calculus and say that the operator commutes with all projections. So, that part is important, okay, and that is non trivial in the case of normal operator. So, we have to prove that. Okay, so, let me write it down. So, this is called Fuglede's theorem. Fuglede's theorem. So, that is the first step. After that everything will follow exactly from the self adjoint case, right, because we did this for a single normal operator by using the result for two self adjoint operators. Once we prove Fuglede's theorem, we can deduce the result for n normal operators commuting from the result for 2n commuting self adjoint operators. Okay. So, Fuglede's theorem, if T is a normal operator on H. So, that means T star equal to T star T commutes with T star, right, and let us take any bounded operator on the Hilbert space. So, X is an arbitrary bounded operator on the Hilbert space such that X commutes with T. So, T x equal to X t, okay. Then X also commutes with T star, then X T star equal to T star X, right. So, X commutes with T implies X commutes with T star, provided T is a normal operator. Okay. In general this is not true, but for normal operators it is true. So, roughly speaking or heuristically this is true because T star is a function of T, right. This is what happens with normal operators. Because of the functional calculus, T star is the image of the function z going to z bar on the spectrum of T, right. So, if something commutes with T, it is what we are trying to say is it commutes with all functions of T, in particular it commutes with the function z going to z bar, which gives me T star, right. That is what is happening. Of course, to prove that we first prove this and then we prove that X commutes with all functions of T. Okay. Alright. So, this proof we will do in a slightly different manner. It will also allow me to introduce something new which is not too difficult, and we did not introduce that in the beginning. Okay. So, proof, if A is a bounded operator, okay, we can define its exponential, right. Just like a matrix, you can define the exponential of an operator. So, define, well, how will you define the exponential of A? So, e to the A you write as a series, right. So, summation n equal to 0 to infinity a to the n is another operator divided by n factorial, right. So, this sometimes we will also write exponential of A. The series converges, right. So, the series converges in the operator norm. So, note that summation n equal to 0 to infinity norm a to the n. So, I am taking the norm inside. So, I want to say this series converges in the operator norm. Okay. So, these are operator norms. Okay. So, this is less than or equal to summation n equal to 0 to infinity norm a to the n by n factorial, which is e to the norm a, right. So, it converges, right. So, it converges absolutely in the operator norm, and so the series will have to converge in the operator norm, right. So, it converges to some bounded operator which we call e to the a, right, or exponential of a. Okay. So, check that. So, most of the properties you have seen for exponential function will be satisfied, but there is no commutativity. Remember that e to the x into e to the y is equal to e to the x plus y. Such things are not true always, but if they commute it will be. So, check that if a b equal to b a. So, that means a and b commute, and a and b are of course bounded operators. Okay. So, a b are bounded operators, and if a b equal to b a, then e to the a plus b, well you want it to be e to the a into e to the b, okay, which is also equal to e to the b into e to the a, because they commute. Okay. So, this is true only if it is commuting, okay, otherwise it in general it is not true. So, you have to be careful when you multiply exponentials of two operators. Okay. So, if a b equal to b a, that means a and b commute, then you deal with them just like you will deal with exponential of x, where x is a real number or a complex number. Okay. So, let us continue. Now, since t is normal, so I have defined the exponential of an operator. Okay. Since t is normal, it follows that for lambda in the complex plane, exponential of I lambda bar t. So, lambda is a number, t is an operator, right, plus lambda t star. Okay. We will see why all this is needed. So, it is exponential. So, e to the I lambda bar t plus lambda t star. Okay. Well, what is this? Because, so if you look at this operator lambda bar t and lambda t star, lambda is a constant, do not worry, t and t star commute. So, these two operators commute. So, e to the, so it is like e to the a plus b, a and b commute. So, it is e to the a into e to the b, right. So, it is e to the I lambda bar t, right, the exponential of I lambda bar t times exponential of I lambda t star. Since, so again, since t commutes with x, right, we want to show that t star also commutes with x, right. So, t x equal to x t, we get now you can do this for t to the k as well, right. So, t to the k x will be equal to x t to the k, right, each time one t goes to the right hand side, right. But then you can sum up, remember the exponential of t is, or exponential of a is summation e to the n by n factorial. So, you can sum up and you can get exponential of t, or you multiply t with constants and then take the exponential, right. So, we get, so this is true for k equal to 0, 1, 2 etc. We get e to the I lambda bar t x equal to x times e to the I lambda bar t, okay, or okay. Now, I want to write x, okay. So, let me write down then and then see why this is true. It is e to the I lambda bar t x into e to the minus I lambda bar t, okay. So, why is this true? Well, if I have a bounded operator a, I have e to the a, right. Now, a and minus a commute. So, e to the a plus minus a, that is e to the 0, e to the 0 is 1, right, from the series expand, 1 meaning the identity operator. So, e to the a times e to the minus a, because they commute. So, let me write down identity equal to e to the a plus minus a, which is equal to e to the a into e to the minus a, right. So, exponential of an operator is invertible, that is what this means, and e to the a into e to the, its inverse is simply e to the minus a, right. So, here I have exponential of this operator I lambda bar t. So, I bring it to the left hand side, I will get e to the minus I lambda bar t, right. So, x will be equal to this expression on the right hand side. Okay. So, now define the function f lambda, capital F lambda. So, this is for lambda in the complex plane, right. So far we have been taking any lambda in the complex plane. So, f lambda equal to e to the I lambda t star. So, now I am taking it slightly different from what we have been doing, e to the minus I lambda t star. Okay. Okay. So, I take this function, we are going to study this function, but before studying the function we use this expression for x and then put it here. Okay. So, x has that expression, we put it there. So, this is simply e to the I lambda t star, okay, and I have e to the I lambda bar t x e to the minus I lambda bar t, right, that is x now, right, e to the I lambda bar t times x times e to the minus I lambda bar t, that is actually equal to x, right. So, this is equal to x. So, I have not done anything, times e to the whatever was there e to the minus I lambda t star, right. This is equal to, look at one term here, this is the, if you look at what is at the top, that is t and t star, they commute. So, when I multiply exponential of these two things, I can add them up at the top, right. So, I will get e to the I lambda bar t plus lambda t star, right. I just change the order, that is all, because that can be done, they commute, x e to the minus I lambda bar t plus lambda t star, okay, the same thing. Okay. So, one comes with e to the I something and the other comes with e to the minus I, the same thing. But the whatever is in the bracket in the top. So, note that lambda bar t plus lambda t star. Well, what sort of an operator is that? Lambda bar t plus lambda t star is self adjoint, right, because if I take the complex if I take the adjoint of this, lambda bar becomes lambda and t becomes t star, and so I will get that this to be a self adjoint, right. So, this is self adjoint. So, if it is self adjoint, if I have a self adjoint operator, what happens to I times that and the exponential of that. So, let us look at that separately. So, let us say A is self adjoint. So, A equal to A star, okay. Look at e to the I A. E to the I A I want to say is unitary. Okay. Well, that is actually easy because you can think of A as multiplication by x, right, on the spectrum, that is in the real line. So, e to the I A will be multiplication by e to the I x. So, its modulus is 1. So, it is a unitary operator. You can also prove it directly because e to the I A into e to the minus I A is the identity operator, right. But e to the I A, what is e to the minus I A? So, this is e to the I A star, right, the adjoint, because A star. So, this is a series, right. So, you look at the series, A star is A. So, that does not change, because of the I it becomes minus I, and though you will get this. So, if A is self adjoint, e to the I A is unitary, right. So, because this operator is self adjoint, we know that e to the I lambda bar t plus lambda t star. So, that is your self adjoint operator in the bracket. I look at e to the I times that self adjoint operator, that is unitary. Okay. So, I have this unitary operator here and I have its inverse here, right. So, x is conjugated by a unitary operator, right. So, I have u x u star, that is how it looks like. So, if I take the norm of, so hence the norm, okay. So, I will stop in some time. So, hence the norm of f lambda. So, remember f lambda is a operator valued function, right. For each lambda we define this function, right, and we saw that it is equal to some unitary with respect to which depends on lambda multiplied by x and the unitaries conjugate. So, when I take the norm, it is going, the unitaries will disappear and you will get the norm of x. So, that is a constant, Okay. So, now we are going to say that f lambda. So, if you look at the expression for f lambda, that depends only on lambda and the t, right. You will see that it is a analytic function, holomorphic function in lambda. I will justify this in the next class, but its norm is constant, right. So, in particular it is a bounded function, bounded holomorphic function for lambda in the whole complex plane. Okay. That means, it is an entire bounded function, operator valued, but then by Liouville's theorem it has to be a constant. So, we will justify that. Okay. So, claim lambda going to f lambda is entire. Okay. So, well, I should tell you what it means by saying it is an entire function. It is a holomorphic function taking values in the space of operators. So, there are various ways of defining it. We did one such definition in the beginning when we dealt with the resolvent. You can use this as well. So, lambda going to f lambda, lambda is in some domain, these are all operator value, right, is said to be holomorphic, is said to be analytic or holomorphic if for every u and v in the Hilbert space H, the function lambda going to, so lambda is in some domain in the complex plane, you look at f lambda, that is an operator, apply it on u, take inner product with v. So, that goes to complex plane. So, this is a complex valued function on the on some domain in the complex plane is holomorphic in the usual sense. Okay. All right. So, we will stop here, we will prove that lambda going to f lambda is entire and so is a constant, and so is a constant by Liouville's theorem. Liouville's theorem. Okay. So, we will stop here. We need to prove that the function lambda going to f of lambda is actually entire using this definition we have just seen. Okay. So, the definition is that lambda going to f lambda acting on u inner product with v is a holomorphic function, and we will, because f lambda is bounded, this is going to be bounded for each u and v, and that will tell me that there is a fixed operator A such that f lambda is equal to that operator A, and we will differentiate that, and from that we will get exactly what we want, that the operator T commutes with x. The operator T and T star, both of them commute with x. Okay. So, we will stop here.